the last point that we saw during the last lesson was the final expression for the interaction term between electrons and phonons. And in that case, let's say the average value of the energy due to that interaction was equal to the summation over Q, G, S, and K. We had a coefficient that was depending on Q, G, and on the polarization. Then we had C cross Q plus K plus G, distraction operator for wave vector K, and then we had the creation and distraction operators for phonons, one with wave vector minus K and polarization S, and the other one with wave vector K and polarization S. And we saw that those two terms corresponding to two different processes concerning this electron, let's say the initial electron with wave vector K and the phonons. In one case, we considered the initial electron. I say initial because here we have a distraction operator for electron with wave vector K, so we need to have that electron in the system, otherwise this term is equal to 0. So in the first case, so when we consider C plus Q plus K plus G, C K B cross minus K S. So in this case, we have the creation of one phonon with wave vector minus K and polarization S, and the electron after this interaction has a wave vector that is equal to K plus Q plus G. The second step is C cross Q plus K plus G, C, K, and B, K, S. So in this case, we have the initial electron K, the phonon with wave vector K and polarization S is destroyed, so that is absorbed by the electron, and then we have the final state for the electron that is indexed by Q plus K plus G. Okay, sorry, here I have Q. Yeah, otherwise, yeah. So this is Q. And this, okay, and this is Q. So the idea is that let's say this process, during this process, we have the crystal momentum conservation, since here the initial value of the crystal momentum is h bar k for the initial electron. Then we have that after the interaction, we have that the final wave vector, final crystal momentum is h bar k plus h bar q. Then we have minus h bar q due to the phonon and plus g times h bar. So in this case, the final momentum is h bar k plus h bar g. So the momentum is the same within a vector belonging to the reciprocal lattice that is g. And here we have exactly the same situation. So the initial momentum is the momentum due to the electron, h bar k, and the phonon. So we have h bar q. The final value is h bar k plus h bar q plus h bar g. So also in this case, the value of the crystal momentum is exactly the same within a value of the crystal moment of the within a value that is h bar g, where g is a vector belonging to the reciprocal lattice. During both interactions, apart from the this crystal momentum conservation, we have also energy conservation. So in this case, we have that in this case, the initial energy of the electron is slightly decreased due to the creation of a phonon, and in this case, the energy of the initial electron is increased due to the fact that we have the absorption of a phonon by this electron, so the energy of this final state will be slightly larger with respect to the energy of the initial state. Okay, and why is it possible that one electron may create or absorb a phonon during its motion through the system? Because if we consider the lattice, so if this is the, let's say, if this is just a portion of the lattice, and then we have one electron traveling through the lattice, then what we have is that the electron is a negative charge, the ions are positive charges. So when the electron moves through the lattice, there is an attractive force between the electrons and the ions. So the fact that this electron is traveling here may induce all the ions here to be, let's say, attracted by the fact that we have a negative charge here that is traveling through the system. So due to that, the electron may or excite, as in this case, or absorb an oscillation or a phonon of the crystalline lattice. So this fact is, again, the possibility to have this interaction is due to the Coulomb interaction. In fact, if you remember here, within this term, we have the Fourier transform of the interaction potential between electrons and ions. So the fact that the fact that one electron may induce this kind of motion into the lattice is explained by the fact that we have V, Q plus G within this coefficient G, and G is the coupling constant between electrons and phonons. So this term here represents, let's say, or is related to the strength of the interaction potential between, to the strength of the interaction between electrons and phonons. And later, when we will discuss the effect of that over the resistivity, we will see that the decoupling constant is related to the scattering rate that is associated to this kind of process. Before going on with the description of what are the effects of the electron-phonon interaction over the dynamics, in particular over the dynamics of the electrons, I would just like to add now that we have the opportunity to add a comment concerning the fact that we have a conservation. Let's say this is another situation where we have the conservation of crystal momentum but not, let's say, strictly, but within an additive vector G, where G belongs to the reciprocal lattice. This is something we have already observed in the past, and we will see also that later, wherever we have the interaction between, let's say, electrons or phonons with with themselves or with the external fields or forces. For instance, when we will see the interaction between electrons, phonons, and photons, or electrons, phonons, and other external particles. We'll consider in particular the case of neutrons. So in this picture, we always have to consider that the conservation of crystal momentum is not strict, but is always within an additive vector G. In general, conservation laws are related to symmetries of the Hamiltonian. And in this case, let's say, if we write down the full expression of the Hamiltonian, we have to consider both the electron contribution and the, let's say, ions contribution. So the full Hamiltonian is, for what concerns the electrons, a sum of, I just write the, let's say, the momentum operator in this way, just for similarity with the ionic one. So we have this contribution due to the kinetic term of the electrons. Then we have the interaction potential between the electrons. Then we have the kinetic contribution of the ions. Then we have the ion contribution. And in case we consider the ions to be, let's say, oscillating, or in case we consider the non-static approximation, here we have to include the, let's say, Bravais vector plus the displacement. And then we have the same condition for the second vector, r prime. So this is the, let's say, electron contribution. The second part here is the ionic contribution, and then we have to consider the interaction between ions and electrons. So we're supposed to have this interaction. For the moment, I just write W. So here we have to consider the coordinate of one electron and the coordinate of the ion, considering also the displacement due to the fact that we consider the non-static approximation. If we now consider this Hamiltonian and apply this transformation, so if we suppose to shift all the coordinates by a vector of the Bravais lattice, so if we now make a translation and in this case, the translation is made by translating everything by a vector that belongs to the Bravais lattice. So in this case, we have the Hamiltonian H prime. So in this case, we have always the kinetic term of the electrons. Then here, nothing changes because both coordinates are shifted by the same amount. So 1/2. Then here we have a summation over, now R is a coordinate, is the coordinate of one ion in position R. So if we translate everything by R0, here we have R plus R0 divided by 2m. Here we have to apply the same translation. So we have R plus R0 plus U of R plus R0. And then we have the same term here. So we have minus R prime plus R0 plus U of R prime plus R0. And then we have the last term okay. So the terms, if you notice here, this term here and this term here disappear because we have a plus sign here, a minus sign here. This term here and this term here disappear due to the fact that we have the plus sign here and the minus sign here. So the only terms that include the fact that we have a translation of R0 are the kinetic term and the displacements. So this one here, and this one here. So if we just apply a translation, then the Hamiltonian H prime is not exactly equal to the initial Hamiltonian H. So we have to apply a second transformation to, let's say, go back to the initial Hamiltonian. And the second transformation is a translation of the, let's say, from the ionic coordinates. So we have to so if you apply this translation here and you also apply this transformation and this transformation, then you observe that the effect of the translation is this one here, and the effect of this transformation is to transform this R plus R0 into R, and this U of R plus R0 into U of R. So the idea is that if, let's say, a uniform translation of overlay coordinates and just this transformation applied to the ionic coordinates brings back the Hamiltonian to the initial configuration. So this is, let's say, the symmetry of the Hamiltonian that is related to the crystal momentum conservation. And the fact that the crystal momentum conservation is not conserved strictly, but is conserved within an additive vector G is related to this fact. When you, I don't want to enter into details of the calculation, but the point is that when you apply the transformation concerning the ionic coordinates, you have terms that are in this form. So when the second transformation concerning the ionic coordinates is applied to the Hamiltonian, then you have coefficients that enter into this calculation that are in this form. So you have a general wave vector k multiplied by R0. In case you have coefficients like this one here, then this is exactly equivalent to e to the I k plus g times R0. Because, and this is just due to the definition of vector G. So whenever you have a coefficient that has this shape here, then the same conditions that can be applied when you introduce these coefficients here can be applied when you use also these coefficients here, when you add an arbitrary vector G to the phase, in particular to the wave vector side of the phase. So the combination of that transformation and the fact that that transformation is applied to coefficients like this one here, where you may add or subtract any arbitrary vector G belonging to the reciprocal lattice, are so that the at the end, the let's say, the crystal momentum, the total crystal momentum is conserved, but only within a vector G belonging to the reciprocal lattice. So when I write total crystal momentum, that means that you have to consider both the summation over the, let's say, wave vectors of the electrons. So for any electron, you have h bar k, and you have a factor 2 in front due to the fact that any wave vector k may be occupied by two electrons with opposite spin. And then you have also the summation over the contribution that is due to the phonons. So in this case, total crystal momentum means both the momentum of the electrons and the momentum of the phonons. So this is conserved just within a vector belonging to the reciprocal lattice. So going back to the previous equations, in that case, we just considered interaction between, let's say, one electron and one phonon. So in that case, the contribution to the total crystal momentum coming from all the other electrons and all the other phonons is unchanged. So the only change may be due to that electron and that phonon. So in that case, we just concentrate on what happens to their crystal momenta. So in that case, the crystal momentum during the process is, again, is not strictly conserved, but is just conserved within a vector belonging to the reciprocal lattice. Now, what I would like to do is to concentrate for a while on, so this part here just concludes the parenthesis concerning why the crystal momentum is not strictly conserved. Now, going back to the coefficient G depends on Q, G, and S, and the expression for G is the following here. So we have the so this is the expression for the coupling constant that rules the interaction between electrons and phonons. Let's say I will use the next topic will concern the effect of the electron-phonon interaction over the resistivity. So what I would like to do now is to discuss this term in view of its application in the topic, again, concerning the resistivity of in particular of a metal. And in this case, what I would like to do is to discuss what is the value of this coupling constant in the limit of low Q values. Later, you will understand why I use this limit. But for the moment, let's just discuss what happens to this term when the value of Q is small. Before going on, let's just focus on G. The fact that G here is different from 0 means that when we consider the electron-phonon interaction, then the final value of the crystal momenta of the system that is formed by that electron and that phonon is not exactly equal to the sum of the initial crystal momentum, but the final value may include the contribution coming from this additional wave vector G. So how may we represent this the contribution of G, or the contribution of G on the interaction? So let's just suppose that we have one initial electron with wave vector K. Just for simplicity, I represent that electron by using the Fermi sphere. So I suppose to have just 3 electrons, so the drawing is simple. So in this case, we have the, let's say, first Brillouin zone, then we have the Fermi sphere, and let's suppose that this is the wave vector, the crystal momentum that represents the initial electron. Then in case we use a vector g that is different from 0, then we have to consider that here, due to the periodicity of the electron energy, then we have another Brillouin zone here. So if we consider the final state of the electron, the final state has to be, I just write, okay. So if this is the initial state, then what we have is, if for instance, we suppose that if we consider this process, so that is described by this operator, so we have k plus q plus g, c k, and b k s. So the effect of this process, b q s. So what we have here is that the initial electron k absorbs one phonon having a wave vector that is equal to q, and due to that, the final wave vector of the electron is k plus q plus g. So what happens here is that if I need this g, this means that k plus q is in the second zone or in another zone in general. So the situation is, for instance, the following one. So I have that this is q. So from the initial point, the electron moves in the second zone. So if we fix the, let's say, if we want to represent all the wave vectors or crystal momenta of the electrons just in the first Brillouin zone, then for periodicity, this point here is equivalent to this point here. But for this translation, we need a vector belonging to the reciprocal lattice. So we have k plus q plus g. So this is a vector, let's say k prime belonging to the first Brillouin zone. So the fact that we may need G is due to the fact that due to the interaction with the phonon, the final value of the wave vector of the electron may not be in the first Brillouin zone, but may jump to the second one. So to bring everything back to the first Brillouin zone, we need G. So in general, you may appreciate from this diagram, then if you need G, this means that the contribution of Q of the phonon is strong enough, or sorry, that the contribution of the wave vector due to the phonon is large enough to let the electron jump from one point here on the Fermi sphere to another point that is not in the same zone, but is in another zone. Here, this example is just on the second zone. So the point is that if you need G, Q has to be long enough to connect this region with that region. So in general, the presence of G means that you have the modulus of Q is large. In general, if the modulus of Q is large, this means that the energy of the phonon is large, because when we represent the phonon dispersion, we have that if this is pi over a, the here minus pi over a, then the energy increases as the wave vector increases. So for large Q values, you have that the energy of the phonon is up here. So in general, the large modulus of Q means a large energy for what concerns the phonon. But if let's say, if the idea is to discuss this term in the limit of low Q, that will be useful later for the discussion, then in this limit, let's say, the value, the modulus of the wave vector of the phonon is expected to be small, and also the energy of the phonon is expected to be small. So in this case, the probability to observe this kind of process is reduced, is quite low. So due to that, in the evaluation now, I will suppose that the G, so I make the hypothesis that G is equal to 0. So if I make this hypothesis, I suppose that these processes like this one here are not observed in the system. So I suppose that, for instance, if we consider the contribution of a phonon, that contribution is small, for instance, like this one here. So the phonon just, let's say, slightly changes the value of the initial wave vector for the electron. So the final value for the wave vector is here. So we have to consider that this is Q and this is K plus Q. So at this point, everything happens in the first below n zone, and we do not need the additional G to represent the full situation in this case. So in this approximation, G equal to 0 S is equal to square root of n square root of 2. Then we have h bar divided by the ionic mass omega s of Q. Then here I have just Q, scalar product A, Q, S, and V of Q. Now, what about this scalar product here? This is the scalar product between the, let's say, Q, that is the wave vector of the phonon, and E, QS, that is the, let's say, polarization vector discussing the direction of oscillation of the ionic perturbation when the phonon propagates through the system. In general, it is possible to, let's say, fix the polarization vectors so that one vector is parallel to the propagation vector, and that is in this case is Q, and the other two polarization vectors are orthogonal to Q. So we have one longitudinal motion and two transverse oscillations. So in general, let's say, this is not always possible, but in simple situations or in isotropic crystals, this is the case. So when we consider this scalar product, only one term will survive from this scalar product, and that term is the related to the longitudinal phonon. So in the leading term, the leading contribution in this coefficient will just come from the longitudinal phonon between the three possible polarization states that we have in the system. And now, if we also consider what happens for low Q values, what happens is that within the parentheses we have h bar, then the ionic mass. Then here we have omega s of Q. Omega for small Q values is proportional to Q. So we have a linear relationship between omega and Q. So we may write that omega is a C times Q. So, and then we have the 1/2 power. Here we have just Q. In this case, let's say, just to stress the fact that after the scalar product, this is not a vector, but this is just the projection of Q over E. But if they are parallel with each other, this is just the Q modulus. And also in this case, omega is proportional to Q. So I stress that the fact that here we have the Q modulus. Then we have V. V is the interaction potential between ions and electrons. In this case, we may suppose to use not the, let's say, Fourier transform. So this is the Fourier transform of the interaction potential. We have observed that due to the presence of the electrons, the interaction potential is not the pure Coulombian one, but is the Yukawa one. So if we write the Fourier transform of that, we have ZE divided by E0, and then we have 1 divided by Q squared plus A0 squared. So in the Q close to 0 limit, then we may, let's say, neglect this Q squared with respect to K0 squared. So what happens is that here, within this parenthesis, you have a term that is 1 divided by Q modulus to the 1/2, to the power of 1/2. Then we have Q modulus here, and then we have just coefficients, because ZE divided by E0 is a constant, and here we have just 1 divided by K0 squared. So in the low Q limit, let's say, this coupling constant is proportional to the square root of Q. So this will be important, as again later we will use this situation, this condition, when discussing the properties of the effects of the interaction between electrons and phonons. Okay, so at the moment we have seen what is the effect of the electron-phonon interaction. We have seen what is the coupling constant during the process. At this point, one interesting thing is to see what happens from what is another consequence from the physical point of view on the electrons due to this kind of interaction that they have with the ionic oscillations. That means with the phonons. And to observe that, we may just go back on the diagram that was that I drew before. I just replot that here. So if we consider if we had a Fermi sphere, one initial electron with wave vector k, and let's just consider the same situation that I considered before. So let's just consider this term here. So this means that we have that this electron with the initial wave vector k interacts with the phonon with the wave vector q. And due to this interaction, we have a new state for the electron that is addressed by k plus q. In this case, as it happened before, the final state has to be a possible final state for the electron. So in general, the final state will not be up here where we have just empty states, will not be within the Fermi sphere, because within the sphere we have just occupied states, but that will be close to the Fermi surface. So let's suppose that, for instance, the final state is here. So we have that this is k plus q, and this is the wave vector q of the phonon. So in this case, we just move from this point to the other point on the Fermi surface. The fact that why is this possible? I just write down the both the crystal momentum So in this case, we have the final momentum, final crystal momentum for the electron due to the absorption of the phonon is equal to the sum of the crystal momenta of both the initial electron state and the phonon. In this case, again, I'm always in the condition G equals to 0. So I'm always supposing that that kind of processes involving G values that are different from 0 is not happening. So, and in this case, this is satisfied. But we have also to satisfy the energy conservation. So we have that the energy of the electron in corresponding to crystal moment wave vector k prime is equal to the initial energy of the electron with wave vector k plus, in this case, because we have an absorption process, the energy of the phonon that is absorbed. In this condition, let's say, so we have two equations that have to be fulfilled. What we know is that K and Q that are related to the one to the electron and the other one to the phonon are vectors that are defined in the same volume, let's say, because both belong to the first Brillouin zone. So in principle, K and Q may have more or less the same order of magnitude because they are, let's say, they are similar vectors. They are defined due to the same boundary conditions, so they are similar with each other in general. But if we consider the constraint concerning the energies, in this case, we have that let's say, that the energy of the electron is larger and larger with respect to the energy of the phonon, because we know that phonon energies are in the range of tens of millieV, while electronic energies are in the range of EVs. So this is larger and larger than the contribution coming from the phonon. So this means that once one electron absorbs one phonon, the change in energy of the electron is nearly zero. Let's say is not strictly zero, but is negligible with respect to the initial state of the electron. So in this picture, let's say the modulus of the wave vector that describes the position of the electron in the first Brillouin zone will not change that much, because let's say if we use the free electron picture as I have done here by referring to a Fermi sphere that is by referring to a Fermi surface that is perfectly spherical, in that case the magnitude of K is proportional to the energy of is related to the energy of the electron. So if due to that the energy of the electron has just a slight change, then also the modulus of K and K plus Q have to be nearly equal. So the point is that, so the consequence of that is that if you start from an electron here close to the Fermi surface, then the final state will have to be again on the Fermi surface, maybe in another point like this one here, but always very close to the Fermi surface. And this also explains why I didn't pick up the initial electron within the zone, within the Fermi sphere, because otherwise you have no opportunity to have available final states for the interaction, because if the initial electron is here, then you have no other possible final states for that interaction, due to the fact that, again, for energies that are very close to this one here, you have no empty states, but you have just filled states. So that's why I pick up the initial electron here close to the Fermi surface, and also the final value for the electron is here, again, very close to the Fermi surface. What is now another feature of related to this change of orientation of the vector that describes the electron state? We know that the velocity of one electron is defined as 1 divided by h bar, the gradient with respect to k of the energy. In case we consider this situation, for what concerns the initial vector k, then we have that v and k is like this here. The final velocity is represented by this vector here, due to the fact that we are always close to the Fermi surface. The modulus of this vector and the modulus of that vector are nearly the same, but what changes is the orientation. So what we observe here is that due to the interaction between the electron and the phonon, we have a change of orientation of the speed of the electron. So the initial electron was moving along this direction, but the final electron is moving in this direction. So you have a sort of, so this is the initial velocity. Then at some point you have an interaction with one phonon, and then you have the final velocity for the electron. So in this case, so here you have the phonon that is absorbed by the electron, and this absorption produces a change in the direction of motion of the electron. And this is what, let's say, Drude supposed to be the effect of a collision. So you have, let's say, he's supposed to have a point interaction between the electron and something else, and due to that interaction, the velocity of the electron could change direction, and this is what happens here. So the change in direction is observed just thanks to the contribution of the wave vector of the phonon, because the contribution of the wave vector of the phonon may help the electron to jump from its initial state to another final state, this on another point of the surface of the Fermi sphere, and due to that, you have this change in orientation, and thanks to that, you have the opportunity to draw this kind of diagram here. So the conclusion of this discussion is that one of the effects of the electron-phonons interaction is that interaction produces, from the point of view of the electron, a change of configuration, in this case a change of the direction of the velocity, that resembles what we expected to observe in case a collision happens into the system. Up to now, we have never been able to single out what is the physical mechanism that produces that collision, because we always supposed to have collisions, but we, let's say, apart from the initial hypothesis that the collision is due to the interaction with a static ion that was not fine, then we never found a mechanism that could explain such a collision. And now we have a source for that mechanism, and that source is the presence of phonons. So the presence of phonons, that are distortions of the perfectly periodical lattice that was used by Bloch to predict the structure of the electronic wave function, produce, let's say, let the wave function of the electron to be no more stable for an infinite time, because again the periodicity of the system changes from point to point, and in some situations maybe the periodicity is even not found due to the presence of lattice oscillations. So due to that, you have a decay of the electronic function from one initial state to another final state, and this decay, this transformation, is induced by the phonon. So or in general is induced by the lattice distortion that is induced by the propagation of a normal mode of oscillation, or in general also to a combination of normal modes that propagate through the system, and so interfere with the perfect periodicity of the lattice. So at this point, we have, let's say, a mechanism that can explain the the source of resistivity, because what we actually observe here is that we have a change of direction of the electron, so we have a mechanism that interferes with the propagation of the electron in a straight line. And due to that, now we have the opportunity to try to explain what is the actual dependence of the resistivity on temperature, because what is experimentally found is that if you plot the resistivity of a system as a function of the temperature, then what you find is that you have a nearly linear dependence here, and then you have a power law here. So what has to be explained is, at first, why do we have this linear dependence here in the, let's say, in general, high temperature and intermediate temperature regime, and then why do we have this power law here when we reach the low temperature regime? And let's say the calculation of this part is not very long, but maybe it's better to do that after the break, so I have the full time to predict the full dependence, discuss about that, and give you comments concerning the of why do we observe this kind of mechanism. So I prefer to stop now the registration.